several visiting positions, which sort of proves that in addition to being excellent at physics, he has also taste in finer things in life, because he went to Paris, where he held 2 visiting professorships at Institut Physique du Globe and École Supérieure de Physique et Chimie Industrielle, where he conducted research in inverse problems as well as wave chaos. It's a pleasure to have him here today to talk to us about his millimeter to terahertz wave work. Thank you for coming, and the floor is yours.
Well, thank you very much for inviting me. I'm having a great time, and it's a wonderful place, and thanks to all who facilitated my visit. Partly this is just to introduce myself to you, because Professor Steer and I have got an incipient collaboration going on, and so I have a feeling I'll be back. And so I'd like to not just focus on one particular area, but just sort of show you a broad swath of what's going on in my group. And hope that if any of this sounds interesting, you'll contact me. Feel free to interrupt me during the talk. So if I lapse into any jargon, just let me know. The picture, we have everything here except a pointer. Do we have a pointer? That's okay. Let's see. Will this work as this will not work as a pointer, I don't think. This work as a pointer? Yeah. Huh, okay. Did I? Well, this picture over here on the left is actually a computer rendering my son did a long time ago. There's a famous picture on the cover of Nature of these mirrored balls, and what you're seeing is actually multiple scattering of light. And so that's been one recurrent theme of the work in my group. Pretty much anything to do with waves we're interested in. Acoustic waves, ultrasonic waves, seismic waves, microwaves. You'll see a lot of millimeter waves and terahertz today. And we do basic science having to do with how you exploit multiply scattered waves, especially in strongly heterogeneous material. And we do a lot of materials characterization using waves. So this is sort of everything, including the kitchen sink. And I'll try not to go over 50 minutes. And hopefully there'll be plenty of time for questions. So this is basically what I just said. We got started in this. I got started in this. Let's see. Is there any way that I can get rid of this little gizmo here? Down here. Ah, yes. With laser ultrasound. And so here's a snapshot in the upper left of actual particle velocity measured with a laser vibrometer in a granite. Can you, well, I sure wish I had a, can you point? Oh, no. We need a pointer. But I just, let's see. If stuff happens when I use the mouse to point. Okay, so in the lower right there, you're seeing a chunk of granite, which is a good example of a random medium. And in the upper left, you're seeing a snapshot from a movie of ultrasonic waves propagating through that granite. If you go to my web page, which is on the very first slide, and I'll leave the slides here for you to use, you'll see the actual movies of the waves propagating through this material. And it's very interesting. At late times, you'll see diffusive behavior of the waves. And we've been able to extract a lot of information from that. And this is a completely non-contacting measurement. So we use one laser to excite the waves, a pulsed infrared laser. So it hits the sample, thermoelastic expansion creates the ultrasonic waves. And we use another laser to actually make the measurements. So, so this is an application more basic science, but we also do materials characterization in the same way. You take the same material and you can mechanically resonate it. And so when you sweep over frequency, when you're resonating one of these things, you'll hit an eigenfrequency of the sample. And the picture on the right shows you an example of one of the low frequency modes of this rock. And from a spectrum of these modes, you can actually invert for the elastic moduli. So here's an example of a spectrum of modes for a relatively simple isotropic material. And so we do this measurement and use the low frequency modes and actually invert for the elastic tensor of the object. Okay? So that's what's called resonance ultrasound spectroscopy. When you get to higher frequencies, you can get some extremely rich behavior when the waves start interacting with the microstructure of the material. And I'm not going to get into that, but that's something else we're very interested in. Now, recently we've gotten heavily into trying to extract the elastic properties and the electromagnetic properties of materials with very high spatial resolution. And this is a technique we're working on right now, actually. So we use a pulse laser, and we focus our laser Doppler vibrometer exactly opposite the point where the source is, and we measure the first arriving waveforms that come across the material. And this lets us get very localized information about the elastic properties. So we can scan the rock, keep the laser beams fixed, and as we scan the rock, we can infer the material properties. Now here is what we've done before using our millimeter wave system. I just wanted to give you a little background. So we've been doing this for a few years now. We take these materials and we scan them, and we use the phase of the transmitted electric field to actually measure the local dielectric properties of the material. And I'm going to come back to this in just a second, but I just wanted to show you what we had done with electromagnetic properties. Now we're doing with mechanical properties as well. So these are actually the same samples, the same piece of granite. And so on the bottom, you see phase perturbations as you scan the sample in front of this millimeter wave, very tightly collimated millimeter wave beam. And on the top, you see travel time perturbations for the lasers. And so the travel time perturbations are telling you about the elastic moduli of the sample, and the phase perturbations are telling you about the dielectric constant of the material. Okay? So that's sort of where we are right now in terms of high resolution. So we can get very high resolution with this technique. Yes?
Measurements.
Oh, do we have a pointer? Excellent. Muchas gracias. Could you repeat your question, please?
On your surface aberrations where you are measurements?
The surface is smooth. So, in fact, so what you do is, for the dielectric measurements, the sample is very thin. And so you bring the beam, the transmitted beam, and the reflected and the reflecting antenna very close together, and you scan through them. So essentially, you've localized the photons in a very small area. And so the transmitted photons are actually not sensitive at all to the surface roughness. They just tell you the travel time through the thickness of the material. Right? So if you were looking at the reflected, if you were doing a scan, I'll show you some later, where you were doing a near field scan, then the coupling of the antenna or the wave to the surface would be a critical factor. But for this measurement, where you're just looking at the travel time of the photons, it's really not. Now here's an example of a project we've been working on for some time. This is an example of active vibrometry, where we, well, just like with the lasers, except we're using a nonlinear ultrasonic array here. This is on mounted on a tripod head, and so we can point this in some direction. And this is a 40 gigahertz interferometer that we use to measure the resulting motion. So the idea is you'll point one at a target to insonify the target, and then you'll point the other at the target to measure the resulting vibration. And so you've probably heard about parametric arrays before, so I'm not going to spend any time on this, but this thing operates at a 40 kilohertz carrier, which you can't hear, but by modulating the beam in a careful way, you can create harmonics, nonlinear harmonics in the air, and that allows you to produce a collimated beam of low frequency sound, which you can point anywhere you want. The advantage of that is that if you try to produce a collimated beam with a linear sound array, you'd need huge speakers, and it would just not be possible. So this is something we built with funding from the Army Research Office, and we take this outside and do tests with it. And anyway, but that's not the main thing. Oh, well, I'll show you some data. What we have found in our test is that we can easily see 1 micron resolution with 1 second of averaging. So if you sit on a point for 1 second, you can see you can resolve 1 second displacements. If you average longer, you can get higher resolution. Okay. So now I'm going to switch to the main part today, which is to talk about millimeter and submillimeter waves and terahertz. So first thing to get out of the way is a matter of nomenclature. A terahertz is 10 to the 12 hertz, right? So at 10 to the 12 hertz, the wavelength of light in free space is about 300 microns. So it's a little less than a millimeter. At 300 gigahertz, the wavelength's a millimeter. So if I'm talking about submillimeter waves, I'm also by definition talking about terahertz waves. But for historical reasons, the term terahertz has become to be used primarily by people coming at this from the optical end of the spectrum. So you can produce terahertz pulses with lasers. For example, if you have a little photoconductive dipole and you hit it with a sub-picosecond pulse, you'll produce terahertz waves. And so in the literature, normally when you hear people talking about terahertz, it doesn't mean it's time domain, it doesn't mean it's CW, it means they're coming at it with lasers. Whereas people who work in millimeter waves or submillimeter waves typically work by harmonic multiplication of microwave sources. Okay? So just FYI. Tons of interesting applications for millimeter waves. For example, look at the energy. At 100 gigahertz, these are 0.4 MeV photons. So they're very low energy. That's why they're great for things like homeland security body scans, because it's very low energy, non-ionizing. If you look at wavelengths, so at 100 gigahertz, you're talking about 3 millimeters. And that's a very convenient wavelength to be working at the lab, or a millimeter. That means that you can produce tightly collimated beams of this stuff, but without the nanoscale tolerances required for optics. The cosmic microwave background is sitting in here. 3 degrees K is at about 300 gigahertz. Tons of interest in meteorology and astrophysics, people who do Rydberg spectroscopy, so lots and lots of applications. Car radars are being built at 50, 60 gigahertz. So just as a historical aside, the first terahertz or millimeter waves were actually produced by people around 1900, Bose and Hertz and those guys. And the field kind of languished for a number of years until World War II. There was a huge impetus in radar work, and in particular in Russia. And so pioneering work in millimeter wave, submillimeter wave technology was accomplished in Russia. And so a lot of it still has not been either declassified or translated. Here's the system we have. It was built by a group, a small company called AB Millimeter in Paris. They're former students or professors at the École Normale, and they were studying basically atomic physics and things like Bose-Einstein condensation. And so this system they developed, it's got a rack of electronics, and you'll see typical sort of microwave plumbing, but at very small scale. These are lenses. So the term quasi-optics is commonly used because the experiments look optical. You know, we have lenses, we have beam splitters, we even do everything on optical benches. So this system is pretty cool because it lets us, in principle, go scan all the way from 8 to 1,000 gigahertz. Our system is currently configured to work between 70 and 600 gigahertz. Everything's phase locked to an atomic clock. So it's not a typical VNA. We have one source and two receivers. So when we're studying a sample, we can measure the amplitude and phase of the reflected and transmitted field. So we can get the complete transfer function of the system. We exploit these things called scalar horns, which are really remarkable devices that allow us to produce a mode that's axially symmetric and vertically polarized. So when we're working in single mode operation, that's what our beam looks like. And it's because of these grooves which cancel the cross polarization components of the beam. So optically, it's a very quasi-optically, it's a very nice system. So here's the quasi-optical setup here. And you can see that we've got one of our horn antennas. We've got a harmonic detector, which works. So let's suppose, for the sake of argument, that we're working at 100 gigahertz, and I'm just going to make up numbers. Let's say that the microwave system is locked on 10 gigahertz, and so we're working on the 10th harmonic of the fundamental microwave frequency. And so on the detector side, that gets the 10 gigahertz gets multiplied by 10 and mixed with the transmitted signal, and the beat frequency goes back down the coaxial cable. Okay? You can't transmit the millimeter waves on coax. They have to be transmitted either in free space or waveguide. Got lens here, sample here, and the way we normally work when we're doing dielectric spectroscopy for bulk materials is we'll do a sweep over frequency, and we'll treat the sample as an open Fabry-Perot resonator. Okay? So as you sweep over frequency, you're going to set up standing waves inside the sample, and those standing waves will allow you to fit for the complex permittivity. Okay? So this is an example where the sample itself becomes a cavity. And you know, there's a nice analytic model for Fabry-Perot. These are what the resonances of a Fabry-Perot cavity look like, and the width of these just depend on the reflection coefficient of the two sides of the cavity. So if the reflection coefficient is fairly small, you still get these nice fringes. So it's still quite easy to do, even with a sample like a rock, which is obviously not a mirror. Okay? Here's some actual data. This is for a piece of rock. And what you're seeing here is the transmitted field, the reflected field. This is amplitude. This is raw data, unfiltered. And then this is the phase. This is the phase of the transmitted field. This is the phase of the reflected field. And the red curve is the actual fit of a Fabry-Perot model. So you do this fit, a least squares fit, and you get the real imaginary part of the dielectric constant, just like that. It's very fast. And so you can do things like watch the paint dry. In this case, watch a rock dry by measuring the dielectric constant of the rock as it just sits on the bench in the lab. We have very low humidity in Colorado, and just watch it dry out. So in this case, you can see this nice linear trend of dielectric constant as the water evaporates. This is, I went out to lunch. I came back the next day just to double check. Okay? So it's really easy, even in a fluid saturated rock. Normally water, well, not normally, but always, water is the bane of microwave and millimeter wave measurements. But in this case, you can see that even in a relatively well saturated rock, we were able to get good estimates of the dielectric constant. Since we can easily measure the phase of the field, it's really easy to measure anisotropy. And so this is an anisotropic material. It's layered. The layering is actually caused by sedimentary deposition. And so it acts sort of like a diffraction grating. And as you rotate the thing in the beam, you can see this beautiful anisotropy that occurs and at different frequencies. So from 110 to 260 gigahertz. You're seeing the phase of the electric field, and as a function of the sample orientation. So we've got a beam that's vertically polarized, and we've got a sample that's layered. So as we rotate the layering relative to the beam, you see the anisotropy. That's right. So that's the rotation of the beam, and this is the extent of the anisotropy. And it gets more anisotropic at higher frequencies because it turns out the waves start to resonate with the layers. So, so a few years ago, we decided we wanted to try to get very high spatial resolution of the dielectric properties because we were looking at materials which were obviously not homogeneous. And so since I had colleagues who do optical near-field scanning, it was an obvious thing to try. So this is our relatively crude attempt at near-field scanning with millimeter waves. So we use a dielectric cone here, and these angles are cut to optimize the critical refraction down here. And this is an aluminum shield to keep waves from diffracting out. And so you got a very tiny hole here. The smaller, the more the higher the spatial resolution. And we've modeled this with finite element. And so if you're interested in all this kind of stuff, like the tip surface coupling, that's in the paper. I'd be happy to tell you about that. But basically, we bring the source field close, and we bring the receiver close, and then we just scan the sample through the beam. And you get all kinds of interesting stuff. So this is what I showed you before, and you can directly correlate the phase changes. So these phase changes correspond to changes in index of refraction, which we've checked with the actual values of the index for the materials in this heterogeneous rock. So we started at 150 gigahertz, and we've moved up to higher frequency. It's very important, for example, in oil shale. I have a lot of colleagues in Colorado interested in that because there's so much oil shale. Oil has a very low dielectric constant. So just by doing these dielectric measurements, we can measure the organic content of rocks much more easily than the traditional way, which is called pyrolysis, where you just burn off the volatiles. And so this turned out to be quite a surprise to them that we could estimate the organic content of their samples so easily. Go up to higher frequency. So all of us, you probably have these RFID cards that get you in various buildings. The nice thing about the millimeter waves is they see right through dielectric. So this is the actual RFID chip inside my CSM ID card. And so we're getting, you can't see it that well on this projection, but we're getting resolution well under 100 microns. And I think we could do much better than that if there were any interest in that. So you can see right through dielectrics, which is one of the real advantages of millimeter waves. I don't know how well this is going to turn out, but this is a fresh viola leaf, and you can see the strong attenuation where there's the most water, so you can see the vascular structure here. It looks a lot better on the screen. But when we got the system running, we were just scanning everything. One of my former students worked for a company in Switzerland that makes almost all the banknotes in the world. So we were looking at some of these variable index inks that they use in these banknotes. Yes. Now, one of the things that's really kind of surprising is that, this is a glass slide cover, not the thick slide itself, which is like maybe half a millimeter or so. This is the slide cover. I forget how thick they are, but they're not very thick. And so when you scan this thing, you can actually see the standing waves set up on the glass slide. And they're caused by the impedance mismatch between the end of the glass slide and the air. So you can set up standing waves, and because it's a rectangular system, it's this perfect sinusoidal pattern in both directions. And so those are just standing waves set up on a piece of glass. Do you understand the geometry? So here's my glass slide, which is probably only 100 microns or 50 microns thick, and we're scanning, on both sides, and the transmitter tip is actually setting up these standing waves on the glass slide. And we have enough dynamic range that we can see that without really any difficulty. Here's a scan of a dime, which has some interesting features. Hopefully you can see them. On the one hand, you can see the classic circular diffraction pattern off the edge of the dime. Okay, so that's just that's a textbook Bessel function right there. But you can also see these modes that are set up within the dime. So there's a rim or a lip around this thing, and this is not a great picture. We have better ones, but you can set up these circular drum modes. And so this is a classic resonance pattern for a circular drum, and it's one of the higher order modes. And I forget which one it is, but you can crank up this mode mathematically, and it fits the data just beautifully. So now here's an example where the probe tip is about a wavelength away from the surface, and that allows you to create propagating waves on the surface. Now, if I move the probe tip closer to within a fraction of a wavelength, it turns out that the millimeter waves coming out of the probe do not couple to waves, propagating waves. They couple directly to the evanescent field. Okay, and that's what is really called near-field scanning. And when you do that, I'll show you that. So here's what you get in that case. And you'll see that those circular drum modes go away. And so this is an image produced entirely with the evanescent field on the surface of the dime. Okay? And this is the thing we modeled with finite element. Okay, so here's something that's also pretty amazing, but it's just textbook stuff, not surprising when you think about it. So you've got a source, and you've got an impenetrable object, a dime, right? And it's been known since the 19th century that if you send a wave at an impenetrable object, you'll get a diffraction effect on the opposite side. It's called Arago's spot, and it was controversial until it was actually measured. But let me show you what you see on the opposite side of the dime. You can actually see these standing waves. And so these are propagating waves or standing waves that are created on the opposite side of the dime from waves that diffracted over the edge. Okay? It's what you would expect, but it's still pretty cool to see. And the fact that we can see this is, I think, a pretty good testament to the dynamic range of the system. Oh, yeah. Oh, you can solve it easily.
Yeah?
Oh, yeah.
And have you looked at any perturbation of such a thing? Say, for instance, I put in a wedge or something like that, and how it affects the propagation modes?
It depends on the kind of perturbation. So for things like wedges have been worked out. It just depends analytically. It just depends on how complicated the perturbation is. But if you have a wedge, that's been worked out. But is that what you meant?
Yeah, any perturbation whatsoever. I mean, in other words, the question is, can you characterize such perturbations?
Well, Okay, so there's a different, so there's, going to a wedge is not a perturbation. That's a big change. Okay, now if you actually are asking about the perturbation for this, like suppose we were to make a small change in, that's all worked out. So that's basically, that's perturbation of the eigenfunctions of this thing. So you can separate variables. You can write down the series solution in terms of Bessel functions, and you can satisfy the boundary conditions exactly, and so you can do the perturbation theory analytically. Now, and so here you have the additional advantage that you can actually tune the frequency so that you can select particular modes. So you don't have to worry about the interference of lots of modes. You can just put it into one particular mode.
Is the excitation source far from the dime and
no.
you're scanning the other?
No, it's still the near field.
You're still scanning
right.
The dime.
So what's happening is actually, this is an example of what in quantum mechanics is called tunneling, because you're producing an evanescent field which makes it to the edge of the dime and then couples to a propagating field. So the waves actually tunnel around the dime, and you get this diffraction pattern. And so we've had, I'm just showing you lots of applications. This is an application I mentioned briefly, this pyrolysis. So the petro scientists are very interested in efficient, quick ways of measuring the organic content. And so this is a sample that we scanned, and basically, I think I have one in terms of dielectric constant and not phase, but basically this is an organic layer, and then they crank up the temperature and burn it off, and they measure the volatiles that come off. That's called pyrolysis. Yeah, here's one. So you can see oil has a very low dielectric, real part of the dielectric constants. It's about a little less than 2. And so these are oil-rich layers here, and then after pyrolysis, it goes away for the most part. But this is a measurement like this we can do in a few minutes. And here's a comparison with acoustic microscopy, which I don't know if anybody cares about, but so I'm just going to go on. Okay. Now, the latest thing in the lab is that we've constructed, we're interested in materials which we can't really measure in our quasi-optical setup, either because they're, for example, nobody has a styrofoam cup. I guess styrofoam's not good anymore, but if you had a styrofoam cup, I can tell you it's extremely difficult to measure the imaginary part of the dielectric constant, the attenuation, because it's virtually transparent. It's so small that you can't even see it. So if you had something like that and you wanted to measure the attenuation, you'd need, surprisingly, a very sophisticated apparatus to measure that. And so one way to do that is to put it in a cavity, a very high Q cavity, so that when you inject the millimeter wave photons, they bounce around a long time. Okay? And every time they bounce up and down, they're sampling the system, and so that gives you enhanced resolution. You can't really see this picture very well, I'm afraid. I should have blown it up. The other thing that actually what's driving this particular project is that we have colleagues who build solar cells, and they're interested in the dielectric properties of thin films. And these thin films are too small for us to see. They're too thin for us to see in our standard quasi-optical setup. So we built a cavity. And so if you could look up underneath here, you'd see this beautiful spherical mirror. And there's a flat mirror down here. It's not finished yet. And you can see that we can move the thing up and down by maintaining, it was very critical that we maintain parallelism in this system. And we inject the transmitted field here, and the field that comes out of the cavity comes here, okay? And so by selecting the distance between the mirrors, we can select the mode spacing in the cavity. And this cavity, our preliminary estimates are that the cavity has a Q of about 500,000. So that means that if a wave or a photon goes in, it bounces around roughly 500,000 times before it fracks out. So that gives you an extremely sensitive measure. And so, for example, if we put a substrate with a thin film in there, with a film on top, and then turn it over, we see a big difference. So that perturbation allows us to actually back out the dielectric properties of the thin film, even though that film is probably 1/5000th of a wavelength. So that's the latest thing. I threw this in because we were talking about scale model building last night at dinner. Unfortunately, I couldn't find the picture. We have a really big one that's like, you know, that would fill up this whole frame here. We had a project that didn't go very far, but we had a project on doing scale model microwave propagation in buildings. And so we scaled the size of the buildings down by 100. And we scaled the frequencies up by 100. And we used 3D printers to produce the buildings. And we have one great whopping building that's 2 stories, and it's got stairs in it and all kinds of cool stuff. But the project never went anywhere, but I still think it's worth pursuing. What you see is that, so what we can do is we can put a building like this on a little, say a turntable, and we can do real tomography. We can do like CAT scanning of the building and actually see little, we put a little Lego man in there to see if we could image the Lego man inside the building. And but one of the key ideas was that when you have a sort of a generically rectangular kind of geometry and you sweep over frequency, these Fabry-Perot resonances show up all over the place. So there's actually a small room over here, and when we sweep, we point the beam in this direction and we sweep, then basically what we see is the effect of the first wall, the effect of the room, and the effect of the back wall. Now, the way to think about this is that if you set up standing waves in the wall, the period is very small, so the Fabry-Perot fringes are going to be very close together. Let's see, the period is very small. No, the Fabry-Perot fringes are going to be very far apart because the period is small. Whereas if you set up standing waves in the room itself, the period is going to be large, and so the Fabry-Perot fringes are going to be very close together. And so this is actually what you get. So when you look at the raw data, this is the Fabry-Perot fringe associated with just the front wall. And so by measuring the distance between these 2 peaks, we could tell the people how thick the wall was. And then by measuring the distance between these peaks, we could tell the people how big the room was. Okay? And so that's the kind of stuff we were doing. But we also put the thing on turntables and did tomography, but I didn't have all that data on my laptop. We have a project to build flexible dielectrics, dielectric waveguides for a space telescope. And so this is just an example of this is operating at 400 gigahertz, and it was ultimately designed to be scaled up to, I think, 2 terahertz. But here's our source. This is a harmonic multiplier. And so we're injecting 400 gigahertz. This is way oversized waveguide, but it was designed so that we only coupled, well, the design goal was to only couple into the TE11 mode, because that's the mode that propagates with the least attenuation. And so, but this is the kind of thing that would be very difficult to prototype at 1.2 terahertz because the tolerances would be so horrendously tight. This is if you just scan, if you just move the source of the receiver, you can actually see this phase change. That's not a big deal. Okay. Now for something completely different. Now this is a scientific issue, and it has to do with the behavior of waves in random media. And there are some extremely curious effects in random media when the scattering is coherent. That means when the scattering events can interfere with one another. So normally in multiple scattering, for example, if you have a glass of milk and you shine light through it, the photons execute kind of a random walk through the milk, but the individual random walks are not correlated at all. And that's, in fact, why you get diffusive behavior. But if the scattering is strong enough, then you can actually cause the individual scattering paths to become correlated. So now, the simplest illustration of this will be in one dimension. So I'm going to show you a series of slides based on an experiment in which we made basically a macroscopic crystal. And these are wafers of quartz and Teflon. So this is amorphous quartz, so it's isotropic, and this is Teflon. The Teflon turned out it's used in cooking. They put cookies on it, but it turned out to be remarkably more uniform than the really expensive quartz wafers we were getting from the semiconductor people. But anyway, that's neither here nor there. So this is like a diatomic lattice, but it's yay big, okay? And so whenever you have a lattice, a periodic system like this, the first thing you should expect to happen is you should expect to see a band gap. And so maybe you probably haven't taken solid state physics, but a band gap occurs when between frequencies where you can just fit a single wavelength in between the two different lattice spacings. And so in this case, you can predict that the band gap is going to be at 90 gigahertz. And what you're seeing here is the reflection coefficient, and this is the transmission coefficient. And so below the band gap frequency, this is essentially the Fabry-Perot response, these oscillations here. But when you hit the band gap frequency, pow, the thing becomes a perfect reflector. Okay? That's as close, this is a logarithmic scale. So that's as close to a perfect reflector as I can measure. And the transmitted field is down by 60 dB. And this is entirely due to multiple scattering. Okay? And the good thing and the bad thing about multiple scattering is that it makes everything incredibly sensitive to small perturbations. I don't have the plot with me, but if we did this, took out one wafer, say one quartz wafer from the middle, then you would create a big defect state right here that goes almost all the way up to 1. Okay? So multiple scattering can be fun, but it can also be pretty scary. Now, so this is for a periodic system. Now what we do is we shuffle the deck to make a random system, and what you see is really striking. Let's see. These are calculations down here, and these are actual measurements up here. And what you see are these modes where the transmitted field is, so this would correspond, for example, to a band gap, where the transmitted field goes down basically to 0, but then zooms up, goes down to 0, and then zooms up. So you see these modes in which there is enhanced transmission, okay, in this random system. And this is a signature of a phenomenon known as Anderson localization. And so what happens is that because of the constructive and destructive interference in this random system, you can create modes which are greatly enhanced at certain frequencies. And so let me show you what those modes look like in this one-dimensional system. Here is, so first of all, I should say that what do you expect generically? If I have a random arrangement of quartz and Teflon layers, the generic behavior for almost all frequencies is if you put a plane wave in, it decays exponentially. For almost all frequencies. That's the generic behavior. Okay? This is non-generic behavior. These are those very special frequencies where you don't get exponential decay. In fact, you get this tremendous enhancement. This particular mode is enhanced by more than a factor of 20. Okay? And this enhancement is caused by just the multiple scattering inside this randomly oriented one-dimensional system. So this is the signature of Anderson localization. So these are localized modes inside the random system. Okay. Now, this is, I'm going to shift gears again, unless there are some questions. Let me pause for a second. Questions? Okay. So now I'm going to show you how, so everything, all the millimeter wave stuff we've talked about so far has been based on taking microwaves and harmonically multiplying them up to high frequency. Okay? Sometimes order 30, 40 to get to high enough frequency. This is a different approach. This is based on using a femtosecond laser and some sort of a Hertzian dipole. Okay? And this I just got from Hamamatsu's webpage. We have everything in place except the two detectors that we need. And so we have a femtosecond laser. And so basically, this is a standard setup for time domain terahertz spectroscopy. And basically, your sample's here, and it's a pulse pump probe kind of thing. And you need two of these detectors. One's going to be a source, and one's going to be a receiver. And this is the little dipole. And you just focus a sub-picosecond pulse on this dipole, and it's going to radiate terahertz waves. So it's really pretty straightforward. Once people figured this out, it became very popular. So that's what we're building, and this will extend our range of frequencies well up into the terahertz. So right now with our system, our millimeter wave, submillimeter wave system, we can cover up to just about 1 terahertz, but these are just different sources and detectors from Hamamatsu. We'll be able to cover well out to several terahertz. So be able to characterize materials out there and actually do incredibly broadband measurements of these systems. And with that, I will stop and see if there are any questions.
For the terahertz devices, was that generated from an FFT? These aren't sweepable sources. They're
the way you do the sweeping on these things is mechanically by moving one of the stages. You have a delay line. So basically what you're doing is you're taking the correlation of the transmitted and the received signal, and you're sweeping one of those by moving a delay line. So you can get incredibly high temporal resolution because stages are so good now, linear stages. Yeah?
How practical is something like this for remote sensing? So for longer distances, you're coupling your field very close, but can you do feet, tens of feet?
Oh, well, for the near field, we were doing that because we wanted very localized material properties. But as you saw on the quasi-optical bench, the sources and receivers are well over a meter apart. And there's no reason to think you couldn't have them 10 times as far apart. It's a matter of collimating the beams and having sensitive detectors. The 40 gigahertz interferometer that I showed at the beginning that we built ourselves, we've used out to distances of 100 meters. Yes?
So the properties of this millimeter waves to go through dielectrics.
Uh-huh.
So why is that? Why can millimeter waves see through dielectrics?
Well, you have to ask yourself what causes attenuation. And the attenuation can be caused by scattering, or it can be caused by molecular transitions. And at these frequencies, if you have a homogeneous sample, there's there's really nothing to cause absorption. And so at least if they're dry. Now, if they're wet, that's a different matter. Water is a very special thing.
So in general, can you say that as the frequency is increasing, the power of seeing through increases, or is it
The power of what?
the penetration of?
Well, what you need to look at actually is the skin depth of the material, and so that's going to depend on the frequency and the conductivity. And so the skin depth will normally get very large at low frequency, but the skin depth for quartz, say, might be a meter or more, right? And so I don't know right offhand, but that's because the conductivity is so low. And so you look like you want to jump in. Yeah, at 100 gigahertz.
Closest to.
Yeah. So in fact, for the measurement, for the localization measurement, we had to characterize the intrinsic and the scattering absorption because we needed a system where the intrinsic absorption, in other words, the imaginary part of the dielectric constant was small enough to neglect. And so we actually carefully characterized the mean free path in those systems. And they were, one of them, I think Teflon was maybe 70 centimeters and quartz was like 100 centimeters. Yeah. So it's amazing. I mean, we can see, we've done measurements where we can see through rocks that are, 15 centimeters thick. And this is with milliwatts of power.
So like glass and things like that would have very large skin depths. In non-conductors.
Right. Right.
And things like bodies have awful, human bodies have awful.
That's because, that's right.
Because of the water.
Because of the water. That's right.
You built a resonator to characterize a thin film.
Uh-huh.
What if you wanted to characterize a gel?
A gel. Well, the first thing is the only reason you build a high Q cavity is to look at low attenuation samples. Okay. So we look at fluid samples all the time. And what we do is we put them in quartz cuvettes. And so basically we calibrate out the effects of the cuvette, put the fluid in, and then when we do the measurement, we get the dielectric properties of just the fluid. Okay? So now you ask about a gel. So the question is, what's the attenuation of the gel? How big an effect is it that we could expect to see? So if the attenuation is extremely small, then you would probably want to use something like a cavity to measure it. But if the attenuation is just sort of run-of-the-mill, then we could measure it with our quasi-optical system. You would just put it inside a sample holder, calibrate out the effects of the sample holder, and away you go. Yeah?
The hemispherical geometry for that instrument, why not parallel plate?
The reason is that, so the question was, why use a hemispherical mirror on top? Why not use a Fabry-Perot kind of geometry where you have parallel plates? And the answer is, if you think about a Fabry-Perot, then any small perturbation in a ray path will walk off, right? And so, you know what I mean? That the ray will eventually diffract out of the between. So Fabry-Perots are primarily used when the two mirrors are very close together. That's right. That's right. That's why you put a hemispherical mirror on top. Now, the other thing you might say, well, why don't you put a hemispherical on the bottom and use a confocal geometry? It turns out, and this was figured out by a very smart Russian about 40 years ago, that the confocal geometry is more sensitive to imperfections in the construction. And so it turns out that the hemispherical resonator gives you very low diffraction losses, and it's relatively insensitive to imperfections in construction.
For your nonlinear acoustic columnator, sound pressure levels, or you have for air to be, it's air, it's the nonlinear medium.
Well, any medium is nonlinear if you drive it hard enough. And so to be honest, our sound pressure level meter does not work at ultrasonic frequencies. We can measure the sound pressure level that we generate by the demodulation, but we can only estimate the sound pressure level of the carrier. And it's got to be at least 125 dB. Okay? So you have to be very careful when you're working near this because you can't hear 40 kilohertz. But
Interact with human body at all?
yes. That's why I said you have to be very careful. So, right. So if you were to be so unfortunate as to put your ear in front of the array, for just a few seconds you'd hear buzzing. But you could permanently damage yourself. And the analogy I always use is hang on a second, is infrared light. And so infrared lasers you can't see, but they can permanently damage your... You wanted to jump in.
Well, I mean, Holisonic manufactures these for commercial applications where people stand in a 120 dB, 40 kilohertz carrier all the time.
I wouldn't want to. And I will not let my students do that. So I...
No, I mean, it's just... We debate on the safety of ultrasonic...
Listen, when it comes to your ears, better safe than sorry. It's like a laser. And so the thing is, when you get into lasers, then there's a very well-defined standards manual that tells you how to compute the maximum permitted exposure for any kind of laser, any wavelength, Q-switched, you name it. As far as I know, such a thing does not exist for ultrasonics.
No, it's hard to find, right?
It's hard to find, and so if I were you, I would wear hearing protection anywhere downstream of such an instrument.
So those kind of services, so maybe medical people who have the best control on this. When I talk to them, they say it doesn't exist.
No, I found like one OSHA thing that sort of
But when you
said...
get up to 40 kilohertz, you get about an extra 10 to 15 dB margin because you don't have any resonant structures in your ear.
Like I say, better safe than sorry.
Yeah.
Any other questions? Yes.
Yeah, I wanted to bring up polarization, and the reason I do is because I work with liquid crystals and, of course, in optical microscopy, and we
Right.
tell a lot of information about in films and
Right.
materials from that point of view. So I just wanted to invite you to comment on the possibility of polarization adding some dimension to this.
Well, we use polarization all the time. So one of the reasons I showed the slide of the scalar horn was to illustrate the fact that we do have very clean polarization. And so we can rotate the polarization, we can use wire grid polarizers. The cavity, in fact, that we constructed actually preserves it's pretty tricky, actually. So the cavity has rectangular waveguide going down to within about 60 microns of the bottom of the mirror, and then there's actually copper in a small hole. We don't have to discuss why that is, but it's essentially to increase the Q of the cavity. But the net result is that we maintain the polarization of the TE01 coming out of the rectangular waveguide. And so if you have an anisotropic material in the cavity, we can easily see that. So we've actually tried doing some stuff with liquid crystal displays, seeing if we could do some modulation, polarization modulation, but it hasn't gone anywhere. But so what would you like to?
Well, mostly I guess I'm thinking from the analysis point of view that we often use polarizers in the sense that there's a controlled input and then an output that you could image or that
Right.
detect something, some property about the material.
Right. Well, the short answer is that anything you can do optically, you can do quasi-optically. So there are Faraday rotators that work. So if you wanted to split a beam and illuminate an object with two different polarizations, you can certainly do that.
What's the frequency bandwidth of your detection scheme? I mean, how long are you integrating your signals, or can you do it quickly?
Well, we're integrating over about 500 periods, but that's at 100 or 500 gigahertz. So it's in real time. The actual bandwidth of the detectors depends on which frequency range you're in. So we have different detectors for different ranges of frequencies. Oh. Well, they're certainly, the detectors are, all the detectors that we have are relatively flat across the entire single mode band of a particular waveguide. So if you're working, let's say, at W band, which is 70 to 110, our detectors are pretty flat across that entire, that's the single mode, bandwidth of that waveguide. I don't know what happens when you get up above about 600 or 700 gigahertz. Things get a lot trickier up there.
Just to follow up on that question, I share the same question, but on your sample, when you scan your little sample, so how many points do you actually have to take all around the sample?
Oh, for the near field stuff?
How long does that take altogether?
The slowest thing, these sort of things, it's the limitations are entirely mechanical. It's a question of you've got to. So originally we did it really crude. We just moved point by point. That was very slow. But then we found that we could scan continuously in a line, and that really speeded things up. But the system is so fast that you're really only limited by the mechanical speed of the stages.
That's actually what I was talking to you about last night.
Right.
Basically, how long it takes to actually sweep the sample. And can you imagine then basically using like a flash laser or something like that?
I guess I would have to ask, what is your ultimate objective? Well, but there's lots of different kinds of images. For example, we use speckle interferometry to image the strain in samples, and we can image the entire sample in one shot. Okay, because we illuminate the sample with speckle, and we do some signal processing, and pops out the entire strain field. That's an example. But if you wanted to measure the dielectric properties locally, you have to confine the photons to that local area so that they're not averaging over nearby areas. And that's what takes you a while. So it really just depends on what measurement you want to do.
If you had an array of detectors and an array of sources.
That's right.
Yeah.
That's right. That would be really nice. That'd be really nice. It's expensive. It turns out one of my former colleagues told me about a technique for basically doing a phased array with a single source that we're going to try. But that's the real issue. They're expensive. So, I mean, that's why even at thermal wavelengths, if you buy a thermal imaging camera, it's like, $8,000, and you're lucky if you can get 256 by 256 pixels, right? And so you can imagine if you wanted to have an array of bolometers. Now, people like NASA can do that, but I can't.
Any other questions?